back to the promised example where the class group is more complicated. Example. Here we take R to be the square root of minus 14. Alright, so in this case, again, modulo of 4, this is what? This is 2, no? Which means that the discriminant of R is 4 times, well, the absolute value is 4 times 14, and S is 1. So if you plug everything into Minkowski's bound, you get that M is less or equal than, so M is less than 5, which means that we have to examine the prime ideals whose norm is less than 5. So we have to factor need to factor 2 and 3, okay, into primes. 2, as before, 2 is ramified. So let me erase this and start doing the calculations. Again, the defining equation is x squared plus 14 f of x. Okay, so mod 2, you get simply x squared, which implies that p is 2 is ramified, and it is the following ideal squared, and this is a prime whose norm is 2. Okay, so then 3, to factor 3, we make a small calculation. We have to figure out if minus 14, so minus 14, whether this is a square or not. So so it is equal, this is the same thing as minus 2 over 3, and this is the same as 1 over 3, which is obviously 1. So 3 in fact factors into 2 primes, so you get P1 and P2. And what are those? So modulo 3, you get, right, so x squared plus 14, this is congruent to x squared plus 2. Mod 3, so then this is congruent to x, well, plus 2, alright, so what do I want? 2 minus 2, right, so x minus 2. So when I multiply this, I will get x minus 4. No, wait. So I get x minus 4, which is minus, yeah, so yeah, so this is right. So x minus 4, and minus 4, this is the same as x squared minus 1, which is the same as x squared plus 2. So this is really an equality mod 3. Okay, So again, applying our theorem, we know that this polynomial is the root of this polynomial is really a generator of our numbering. So this is good, which means that we can write what these ideals are. P1 is 3, and then you take 2 plus square root of minus 14. So we'll choose that one as P1, and P2 will be 3, and then you take the other one, so this will be minus 2 plus square root of minus 14. Alright, so what are the relations that we got from our calculations? If I denote this prime by P, what we obtained is that P squared is 1. The norm of each of these ideals is 3, so this is a potential generator, each of them. And we have P1, P2 is 1. Alright, so these are not enough to determine what we obtain, because right, so so we have to work harder to determine the other classes. Okay. What was my bound? So this is, my bound was 4. So and this is 3. Okay, so let me keep these primes somewhere separately so that we can work with them. Let me rewrite our potential generators. So P is 2 square root of minus 14. P1 is 3, 1 plus right. So actually what I got is 2 minus 2. So I had 2 minus square root of minus 14, and then P2 was 3 minus 2 minus 14. Yeah, if I remember correctly, maybe with a plus here, because I had x minus 2, x plus 2. Right. So I wanted to get x squared plus 14, which is x plus 2. So actually, this is maybe easier. Yeah, this is definitely also true. So modulo 3, you have this congruence because you get x squared minus 1, and minus 1 is 2. So really I should have used 1 here. It doesn't really matter. So it's the same result, but just so this is maybe slightly simpler. So we have these three these three ideals, which are potentially generators. Okay. So now, and the norms of those, norm of P is 2, and the norm of P1 is equal to the norm of P2 equal 3. All right. Okay. So what can we say just by looking at having three ideals with these norms? You can't really see what could be the group, yeah, because just knowing that p squared is 1 and p1 p2 are the inverses of each other is not quite sufficient. So we have to see what is the relationship between p and p1. We have to find an extra relationship. So for that, you make an observation that 2 minus square root of 14 is in P. Well, so 2 minus this element is definitely in P, and 3 minus this element is also the same. So 2 minus 14 is also in P1. Okay, so this means that both primes divide this element. So 2 minus square root of minus 14 is a principal ideal, is equal to P times P1, okay, and maybe something else. So now computing the norms of both sides, the norm of this element is 4 plus 14, which is 18, and the norm of P is 2, and the norm of P1 is 3. Okay, so there is some extra ideal here, which should be 3 of norm 3. So there is some ideal here. Norm of pi is 3. Okay, so then this condition implies that, as we know, for example, from exercises, homework exercises, we know that. Let me write this as a remark from exercises. And this is not difficult to prove. This is, I mean, it's almost obvious. So norm of the ideal is inside of the ideal, which means that this I divides 3. So I divides 3. But we know that the only ideals that divide 3, it's either P1, P2, or their product. And to get norm 3, we have to pick one of them, one of those. So this means that if I erase this part, just make sure that you understood why this ideal has to be one of those. From this calculation, we get that I must be P1 or P2. Okay, so let's see if this can be P2. If I is P2, then we get that 2 minus square root of 14 equal P times, well, P1, P2 is 3. Yeah? So this is 3, the ideal 3. This means that 3 divides this ideal. Yeah? But this is not possible. For example, yeah, so I will leave this as an exercise. Since 3 does not divide divide 2 minus square root of minus 14, I cannot be P2. So this is like exercise. You should try to figure out why this leads to a contradiction. If you can't, you can ask me next time when during the next lecture. So overall, okay, so if it cannot be P2, then it has to be P1. Alright, great. So let's see what we get. We get that this is true. Okay, but this is principal. So P times P1 squared is 1. Okay, so now we did get a relationship between P and P1. We know that I think here. So we know that P squared is 1. So this implies that P inverse is P. Okay, but this says that P inverse is also P1 squared. So this means that P is P1 squared. Alright, so this P1 can be used to generate the ideal class of P. Yeah, one thing that you should be careful about, it's not a statement that P1 squared is equal to P. Okay, maybe I should write it just to make sure that you don't get confused. This does not mean imply that P is equal P1 squared. This is definitely false. Okay, on the level of ideals, you don't have this because, for example, the norm of P is 2 and the norm of P1 is 3. And if you compute the norms, you get different numbers. But what this says is that on the level of ideal classes, you do have this equality. Alright, so what else do we get? We get that P2 is the inverse of P1. Okay, we also knew this. So this P1, whatever its order, it generates the full class group. So these two relations imply that the class group of R is generated by P1, by the class of P1. And then the question is, what's the order of P1? So that we have to figure out. Well, the order we we can get a bound on the order, right? Because here we have this relationship. We know that p squared is 1, and since p is p1 squared, we know that p1 squared, so p1 to 4th power is p squared, and this is 1. So the order of p1, or the class of p1, it's either 2 or 4, or p1 is trivial. Okay, so the class group is generated by this, and class group R is either 0, Z2, or Z4. And then this condition, because right, so the fact that this is equal to that, it means that P1, this implies that P1 inverse is equal to P1 cube, which means that P2 is really the cube of the class of P1. But it does not mean that the class of P1 is not trivial, or it might have order 2. Then the class of P1 is equal to P2. So these two ideals would be in the same class. Okay, so let's. It remains to figure out what is the possibility for the order of P1. All right, so we will show that 1 P1 squared and P1 cubed are distinct ideal classes. So then knowing this will help us to once we know this, we will know that the cuspidal divisor group is cyclical for the 4. Now, one thing I should mention, again, you have to be careful when you're dealing with ideal classes, right? So here we have that P2 is, so P2 is equal P1 cube. It does not mean that they are equal on the level of ideals. So you cannot, there is no contradiction to the fact that if you compute the norm, here's what I want to say. If you compute the norm of this ideal, you will get, well, the norm of P1 is 3, so this is 3, 3, which is larger than Minkowski's bound. So then you might say, well, how come this ideal is here? Well, this ideal is not really, I mean, this ideal is here in the sense that its ideal class is here. So in the ideal class of P1 cube, there is an ideal, namely P2, whose norm is less than Minkowski's bound. But the norm of this specific ideal is larger than Minkowski's bound. So there is no contradiction to what I wrote and the theorem that proves the finiteness of the class group. All right, so finally, let's do proof this statement. Okay, so if the order of P1 is not 4, then this P1 squared has to be 1. Yeah? So, if order of P1 is less than 4, then P1 squared is 1. Okay, but if this is 1, then P, which is P1 squared, is 1. So this means that this ideal is principal. This implies that P is principal. Okay, so let's say P is equal to some x plus y square root of minus 14. Okay, now let's compute the norm. The norm of P is, as we know, is 2. Right. The norm of this element is x squared plus 14y squared. Okay, but there are no integers x and y that satisfy this equation, so we get a contradiction. So no solutions. No solutions in integers, and this implies this is a contradiction. So this P is not 1, and so P1 squared is not 1, which means that the order of P1 is actually 4. So after all this work, we do get that the class group of R is generated by the ideal class of P1, and it is isomorphic to the cyclic group of order 4. Okay, so this took me a little bit longer than I expected, but what we will do on Tuesday, I will start actually proving this, and to prove Minkowski's bound, we will need to introduce a new technique, which is quite beautiful. You have to embed the ring of integers into a Euclidean space, into a real Euclidean space as a lattice, and then you can read off from the properties of the lattice the invariance of your number ring. So we will see how that works, and yeah, so this will be the end of the first makeup lecture. Then next week I will probably post another makeup lecture, and that will be 2 of the lectures I missed.